sections and combinatories?
One per section.
Yes. So, or actually, I wanted to review a little more because this exam is coming close. Your problem might also be on induction. So I didn't check you on induction, and that's very important. And then on first two sections. So sections 3.6, 4.1, and 4.2 are candidates for your quiz on Monday.
Sorry, you just spoke about induction, and problem happened in my other class. And I was wondering if we could do that. Getting induction from the last case and work your way down to, instead of working from case 1 and working up for, upper cases, can you start from higher and then work your way down?
Yes, but you have to do it carefully. For example, there is one famous proof. Which one was it for context function? Yes. Yeah, something like this. The function is convex if f of a plus b over 2 is equal to f of a plus f of b over 2 for any two inputs, for example. Then can you prove that for convex functions f of a1 plus an over n is less than or equal f of a1 plus f of an over n? So let's consider this problem. This problem is actually very hard to work from n to n plus 1. But it's easier to work from n to n minus 1 with some readjustment. But that's not logically valid. Because what? What if you start from 20? So from 20 down, everything looks good. So generally, the only thing you prove using that is that it's low, good below 20. Right? But if you want to make it valid, here is a method. It's at the function. Let's say the following. So let us have this. For every n, phi of n implies phi of n minus 1, which is what you're asking. But also phi of an for an infinite sequence an. Then you're okay. Then, for every n. So this infinite sequence doesn't mean for any n. Choose however you want the infinite sequence. So for example, when you do this proof, generally what you prove is the following. Phi of n implies phi of n minus 1. And then you easily show that your statement is true for n equals t to the k. For 2, 4, 8, 16, 32, 64, and that's easy to prove. And then justify. Why? Because
At West, the word order run.
if you have
Someone lost. Someone lost.
So if you have infinite, why? Because if you have infinite sequence, then what? You can use that infinite sequence to get as far as you want, and then downward sweep everybody. And then if your number is higher, then you use infinite to climb higher and sweep down. So, yeah. So this is called a regressive integration. Yes. So it is true, but you must have that infinite sequence of your choice. Then it's valid. Otherwise, no. Just it's valid from your starting point on. You cannot say for everything. All right, next question. Yes.
From the question, from the homework sheet, number 4.
Number 4.
I could do 4. Probably.
All right. How many functions are there from the set of 3 elements to a set of 5 elements? So what would that be? Problem number 4. So here are the objects from A to B, where A has 3 elements and B has 5. So I'm not losing generality if I say that those are 1, 2, 3, and these are K element P cube. K element P. Is that what it is basically? repetition, but also I thought that you learned that well enough in your intermediate algebra and everywhere. So what is a function? I'm doing what? You have domain and a range. Domain when you get inputs, range when you get outputs. For every input, there is only one output. Agree? So here, is it clear what my domain is? 1, 2, 3. Is it clear what my range is? It's clear. Now I want to assign the rule. So what? What should I assign for images? So I need to assign what is f of 1, what is f of 2, and what is f of 3. You agree? How many ways can I choose f of 1? As many ways as I want. That means not mean any member that I want. Here, not as many ways. How many ways? 5. So it could be one of the letters, which means 5 choices. What about f of 2? Why 4? Am I saying that they have to be different? No. Those are so-called one-to-one functions. Then if they said one-to-one function, that means inputs cannot share the same output, but generally, can everybody map into k? Yes or no? Is that a good function? Yes, it's a constant function. It is a function. It's not a one-to-one. So can I choose? Do I have again 5 options? Yes or no?
Yes.
What about the third one?
5 options.
Now my question is, what do I do with these 3 numbers? Should I add them or multiply them? Should we multiply them? Why? Because those are just stages in my process. So I choose this, that's first stage of the process. This is second stage, third stage. I can combine them however I want. Do you agree? That's clearly multiplication principle, and the answer is 5 cubed. And that, by the way, there is one notation in mathematics. How do you represent all the functions mapping one set to the other? This set is labeled like this very often in mathematics. It's a B. Because it's 5 to 3, exactly. You are imagining domain on top, range on the bottom. If you find that notation, when you see set power set, that's all the functions from upper 1 to lower 1. Why did they choose it that way? Because it reminds them number-wise it's 5 to 3. And is there part B? No. So if I ask how many one-to-one functions are there, so what is the difference then?
5 times 4.
5 times 4 times. Exactly. Whatever you choose earlier cannot be then used later on. Next question, again. Yes.
Number 9.
Number 9. Those are again from mathematics. I do harder. All right. Number 9. Suppose, and that's a standard problem from statistics or probability work. So what? Suppose that the fair coin has been tossed 10 times. So last time we talked about 4 times. And we were able to draw the 3. In 10, there are 2 to the 10th outcomes. And of course, we're not going to draw them. But we keep in mind that 4, and we'll just use methodology that we would do on 4. So on 4, you can really visualize things. And here we argue by abstraction. You understand that? That's a common thing, not only mathematics. In many disciplines. So here's what I would say. So number 9, it says 10 times. So I have 2 to the 10 options. 2 to the 10 outcomes. What are they? All heads. Head, head, tail, tail, head, head, and so on and so on. And as I said, all those lists of head and tail got 2 to the 10. They want me to count, not all of them. Those that had at least 8 heads. At least 8 heads. So this is the word that we didn't study. We studied or, but we didn't study at least. Okay? Can I break at least into or language? So that means what?
8 or 9 or 10.
Yes. So at least 8 heads, but I'll start from easier one. 10 heads, exactly 10 heads. Or 9 heads, 1. Is this good enough? Is this acceptable for this?
No, we also need 8.
9 heads and 1 tail. string have 9 heads and 1 tail, and at the same time 8 heads and 2 tails. Can someone be in both categories? No. So why is that important? That's the first question when you see, or your first question is there an overlap or not? So since when I see that there is no overlap, I'll put clear pluses, agree? And then what? Just a count. So this is an easy count, although we'll learn little machineries for this already today, but since we don't have those formulas, let's work with multiplication principle, which is the only thing we got. 10 heads, how many strings have all 10 heads? Only one, just check. Now, if you want 9 heads and 1 tail, how many configurations are there fitting this description? 10. Why? Because if you have 1 tail, what's your only dilemma? Where to put that tail, do you agree? And it could be first, second, third, or 10th. They are all different, so there are 10 of those. Was it clear so far? Now it will get a little tricky. If I need to choose 2 tails, the question is, in how many ways can I choose where to put those 2 tails? What's it? Oh, no. No. Carefully. So, this might be a little premature. We'll learn a configuration where I'll just call formula and be done. But since we don't know that formula, we have to design it ourselves. What would that be? Imagine, well, I always like to draw this, so there are 5 of them, 2, 3, 4, 5, 1, 2, 3, 4, 5. So imagine that we are filling in the blanks with heads and tails, okay? So how many T's do I need to put there? 2. So here is one safer count, but slower. I can say the following. One of those T's will be put first, maybe, and 1 second. One is more left, one is more right, okay? When can be my most left? Can my most left be here, yes or no? So left one, left on 1, if I decide that, then how many options for the right one do I have? 9, because I can feed 9 wherever I want. Second one wherever I want, do you agree? So that's 9. What if I put the left one on 2? Then right cannot go before it because the right goes after left. I have 8 options. If I put T here, there are 8 options for the second one, agree? Then left one on 3, it would be what? Left one on 9. No, on 9, I skipped a little bit. 1. Left on 10, impossible. Then you don't have space. So I'll add this all up. By the way, what do I get? Sum of all numbers from 1 to 9. Do you agree? How much is that? You can use that vowels 3. 45. 9 and 1 is 10, 8 and 2 is 10. Or just add them up, that's 45. The final answer is what? 56. Could I have done this a little quicker without all this? The answer is yes. But we have to explain it more carefully, and as I said, that's more in the flavor of section 3. And here's the way. How many tails do I need to choose? Doesn't matter which is first, which is second. In how many ways can I place the first tail? Can I place it wherever I want? Yes or no?
Yes.
Or can I place it here? Then in how many ways, so I placed 4. And then in how many ways can I place the second one? Everywhere, which is in 10 different ways. Everywhere except on the busy place. So it's how many ways? 9. This way I got 90. A minute ago I got 45. Where I'm, what's wrong this time? Double count. Why? Because if I choose 4 and then later I choose 8, I count it like 4 first, maybe. But if I choose 8 first and then 4, does that matter? Is that the same 2 tails? So that's why I had double count, and that's over 2. As I said, we will learn configuration doing this automatically, but one way or the other, that count is 45, altogether it's 50. And then what? Can we generalize this for any number n? Yes, you can see this is n times n minus 1 over 2. This is n, this is 1. So once you get that, that's why I did the high number, so that you cannot just throw the 3 and count. So this is standard kind of abstraction. 6 is basically the same problem that we did on the board, just with a little trick inside. You have to read everything. So here's the story on number 6. What was the story? What do they play? Football and what?
Basketball.
Football, basketball, and soccer. So this looks like Venn diagram with overlap between the sets. And generally, even if it's irrelevant, probably what maybe will troubles for you to solve this problem is maybe you didn't read the beginning. So what is the total number of students in this school? 100. So here is 100 on my picture. It's not there yet. That's a universe. All students, that's 100. How many of them do not? They didn't ask that. But for orientation, it's always good to fill in little things that you can do. How many of them play no sports? 16. And here are those 84 that play one or more sports. Ready? And then what? I just use principle of inclusion, exclusion. Set the following. Count of football and basketball and soccer equals football, total basketball plus total soccer minus overlaps. FB, I'm skipping intersections. Usually that's what we do. Minus FS minus BS and what? Plus FBS. And then what happens? Usually things are most complicated if this guy is missing. All three of them overlap. But what's happening here? That's the only thing that's missing. Because do I have the union? How much is the count for the union? 84. Do I have total football? What is total football? 42. 42. Because 42 is not football only. They say play football and maybe something else. So 33 play basketball. 35 or swimming team, not soccer. Did I say soccer in the beginning? Okay, swim. Then there is a mistake on that. We need to adjust that. And then what? Double overlap. Where are double overlaps? 11 for the first double overlap, 10 for second, and 9 for third, and plus FBS. So can I get number of those that play all three sports? Yes, that just solved the equation. So what would that be?
Just play basketball.
84 equals what? What is this? 75 plus 35 minus 20 minus 30. So 84 equals 80 plus FBS and plus FBS. How much FBS? 4. And then what? I also have something else. What would that be? How many students play? Oh, how many students play only basketball? So as I said, I first answered B because B is the crucial one. Then if I have that, everything is fairly easy. What? Basketball only. Who's here? How much is here?
9.
Where did you get that 9?
It says basketball and swimming team.
This is basketball and swimming is 9, but 4 are here, so this field alone is what? 5. Because those fields are actually, there are 8 fields, and disjoint fields are always the best for calculation. Who's here? Basketball and football, but no swimming. So how much is that? Basketball minus 4, which is 7. Does it match the story completely? And now basketball alone is what? 7 and 4, 11, and 5 is 16. And total basketball is what? 33, so this is 7. So always count is the best when you have this joint. And as I said, since this triple overlap involved kind of influences everybody, that's what you always look for. Once you have triple overlap, everything is easy. Subtract, and then you get clean field. aggregate numbers, you rarely get clean fields, but when you have triple overlap, then you can easily get out of aggregate number. So this is aggregate for both basketball and swimming, agree?
Yes,
If I have this, I can get easily this guy.
I understand that, but I guess when you say that we don't have a basketball alone, I thought that was the point, that you add the number of basketballs and then take off the overlaps. You know, that play.
I agree. But what happened? You took this guy twice, and then you want to recover that. That's actually again inclusion exclusion carefully. As I said, this is easy. So get a triple overlap from here, everything comes.
So you should reverse the question order then, right?
Doesn't matter. So generally, if I don't reverse the order, that means that's a tricky question. Then actually, it's tricky. If you read this and this one's not there, then you actually have to envision that whatever they ask you, triple overlap is the key. The moment when you have triple overlap, everything is easy. All right, so let's go to today's section. Topic for today is permutations. So what happens, particularly today and on Monday, we'll study two configurations that are very often confused for one another. And it's very important that you understand, not just to learn formula, we'll learn a couple of easy formulas. The most important thing is when you read the text, to recognize which category is it. So, generally, what are permutations?
They're like, when we think about a combination, what was it?
Don't even, please, don't use word combination, because that's reserved words for section 3. So if you want to use string, configuration, use any neutral word, don't use combination, please. Oh.
It's the count of the possible ways to order something, considering their order. So in this case, when you said that we had to delete the overlap, we don't have to delete the overlap, because what order they've chosen them.
Very good. And sometimes from the story, it's not clear if order matters or not. You know? So usually, in contrast to what we'll do on Monday, I talk about the following. So first, before contrast, actually let's talk what is permutation. A precise definition. Let me see the symbol that we use. I think that's simple. So that's PNR. Okay. So let's cover both of them at the same time. You have n elements. We are making a list of R elements where R is less than or equal n. And two important things. Number one, a repetition is not allowed. So that means when you use one of the letters in your string, you cannot use it again. Is that clear? But what if you want to use them? That's then different story. So you know, for this configuration, you can use the formula from this section, or you can call it permutation. If repetition is not allowed, and what else? The order is important. Actually, this part, this requirement is a little bit redundant. Why? Because how we label them. As I said, there are different ways that people label them. We label them P, N, R. So P and R is the number of those configurations or those lists where we start with N symbols or N letters and make a string of R. And getting the formula for this number is quite easy. What would it be? That's just using multiplication principle that we had last time. So what would that be? You say the following: you need to choose R, you need to make R decisions. So here is R boxes. And then what? In how many ways can you fill in the first letter? N ways. Then when you fill in, doesn't matter what you chose, then they all behave in the homogeneous way. That means next time you can choose whichever one of the remaining N minus 1. Okay? So this is N minus 1. This is N minus 2. Now what is the last one? When I choose the R to 1, in how many ways can I do that? That's maybe a little tricky to kind of envision in a general case. What would that be? Let me see. So when I choose the last one, this was R minus 1 are already fixed. Agree? How many letters are left for my last decision? There are N letters. R minus 1 were used previously. How many are left for my last decision? If I had N, I spent R minus 1, so how much is that? N minus R plus R. So that's my last. Very good. So what's then? So this is the formula for PNR. Example. How much is P73? So what is that? I have 7 letters and I'm making strings of 3 letters. Order counts and no repetitions allowed. Is that what it is? So how do I do that? It's what? 7 times 6 times 5. You don't have to plug it in and calculate this. I just do the count. 1, 2, 3. That's when you stop. When your count reaches 3, that's where you are. Or if you want to use formula, 7 minus 3 is 4, plus 1 is 5. That's what it is. And what? What if I want 7 strings of maximal length? 7. What happens then? In how many ways can I make full length string? Where's everybody?
7,
You
6.
go 7 times 6 times 5 times 4. Last one, just whoever's left, because you want to use all the letters. This symbol is famous symbol in mathematics. It's called what? 7 factorial. In this case, we don't write P of n, we just write P of n. So if you see only one symbol, we just say it's P of 7. So you are using 7 objects and you are aligning them. So what is the difference? The difference is when I have full factorial, that means everybody's in the game, you agree? There's no like I'm choosing someone and I'm lining them up. No, either everybody's in the game, that's full factorial, or it's just a few of them are in the game, but you're lining them up, or that's important, then that's PNR. By the way, this famous symbol, 7 factorial, we can use to actually describe those short, I call them often R permutation, I call them often short permutations. How can I describe this? I can say the following. 7, 6, 5.
N factorial minus R plus 1 factorial.
N factorial divided by n minus. It's very good. Why? Because I can say the following. Did I stop? Does it look like I started to write factorial and I kind of stopped? Let me finish. 7, 6, 5, 4, 3, 2, 1. But then what do I need to do? Divide by 4, 3, 2, 1. And that's exactly n factorial, and this is your n minus r factorial. Because if this is n minus r plus 1, next one is n minus r, and n minus r down, that's n minus r factorial. And this is the formula you will find in the book. I never use it for practical purposes because I need to cancel tons of factorials, but it's nice to write down. And that's it. That's the only thing to learn for today. I'm not meaning saying we are done, but formula-wise, that's what we need to learn. So n factorial for arrangement of all the elements, and then n factorial over n minus r factorial for those shorter strings. So a good term for this is string or list or words. Also, when you say words, when you write a word, is the order of letters important? Yeah, so when we say words, we always assume permutations. Just something that maybe I didn't even write in my notes. People usually, when they allow repetition of letters, and they put bar above. So when you put bar above, that means permutation when you are allowed to repeat letters. But for that one, it's easier. If I'm allowed to repeat letters, what does that mean then? 7 times 7 times 7, so you don't disqualify the letter. So here's something very important. So this time we are learning two formulas, one for full size permutation, one for R permutation, and they are useful. That's why we are studying them. But what often happens, people think that just if they learn 3 formulas, then whenever they read a problem, one of the formulas will magically solve it. And that's a really bad way to do that. So the way to use this is to see how those formulas can serve your construction. So you have to design the problem, and when you recognize something that is describable as permutation or short permutation, use the formula. But don't expect the formula to do the problem. There's just one ingredient that's sometimes like a shortcut. The design has to be entirely yours. That means you have carefully to read the problem and to do the design. By the way, I also want, before we start doing problems for the notes, also to mention modeling-wise, how when I see P7.3, what do I imagine? We all have favorite examples, like in foreign language, you have your favorite constructions. So that's here, permutation P7.3. What is that? So that's like 7 objects, and I'm making a list of 3. Okay? So story for that. So story for example. Example 1 is in a class of 7 students, we are choosing a president, a vice president, and secretary. In how many ways can we make the choice? So do you agree, and that's very important that we understand when we read the text, that we recognize that this configuration is applicable. Do you agree that that's applicable?
Yes.
Why? Because we have seven objects, it's hard to say, 7 students, and we are choosing 3, do you agree? Now my question is, do we qualify for P or we don't? That means, is the order important, how we choose them? If we choose John, Mary, and Steve, is it the same as if we choose Mary, Steve, and John? Yes or no?
No.
Yes, it is different. Why? Because when I say, I don't know if I formulated this, John, Mary, but how are they appointed during that choice? Is that clear? And when that happens, then we call the P73 formula. And you will see on Monday, there will be some choices where order is not important, just cuisine. Like if you choose, if I said committee of 3, would it matter who was chosen first on the committee? One they are chosen at the same committee, really. In that case, those will be considered as the same election of the committee. And that will be different configuration than the one we'll discuss. So when we start doing the problems, I want you to recognize if what we are studying today really qualifies for what we are doing. Is that fair? What else? And don't forget, all these principles are made out of multiplication principles. So very often, you can just go and solve things with multiplication principles, not even calling the formulas at all. So sometimes that's the healthiest approach. Yes, sir?
If order didn't matter here, can you do this and divide by 2 again?
Not by 2, by 6,
By 6.
because that's possible shuffling. But that's Monday. Let's not rush it.
Okay.
So we'll talk about it and explain it all in detail. And right now, we want to see that there are some other things, so we don't want to apply what we learned today on those others, community stuff.
So for that, would an example be like if you're trying to roll 2 dice and then you're looking for a set of 2 different numbers on the dice?
Now you see, now sometimes it's actually hard to answer that question. So here it is. Here's a question. I roll 2 dice. And then, 2 dice. How many outcomes? How many outcomes do we have? Yeah, you have to be very careful because, from word problems or mathematics, sometimes some conditions are missing. So, my question is the order important? So first, 36. Why? Because I'm not going to use permutation formula. Why? Because are repetitions allowed? Can I get 3, 3? Yes or no? So repetitions are allowed. I cannot call my formula. My formula only works if repetitions are not allowed. Agree? So, but if they are allowed, that's very easy. 6 options on first, 6 options on second, and that's 36. Make sense? But then you can say the following. And usually when they do probability and everything, they always think 36 and they write all those options. But my question is, if I get 3 and 5, or if I get 5 and 3, would you consider that the same outcome or different outcomes? First, let me say immediately. Did I count them separately here on this 36 count? Yes or no? Yes, because I counted them. Because when 3 was on first, was here counted, and when 5 was on first. So this I gave it a separate count. And you can say, is that reasonable or not? Depends. Depends what you are doing. For example, if that's the game, then it might be that. So sometimes we usually say here, 2 distinguishable dice. Let's say one is red, one is blue. And let's say what's on red is worth $10, what's on blue is worth $1 in some games. So then it really makes a difference how they fall. Agree? But if they are indistinguishable, then for example, you play Yahtzee or whatever, then you might be interested to count them as the same configuration. And it's up to you. You want to count? So even if they are distinguishable dice, then it's 36. No doubt about that. What if they are not distinguishable? Then what would we do? I will divide by 2. You know why? Because there are those 3, 3, 4, 4. There's no double count on them. So I will do the following. 36. There are 6 of those that have double. That have the same number. 1, 1, 2, 2, 6, 6. And there are 30 of those that have different numbers, like 3, 5, 3, 4, 1, 6. And those have double count. Agree? So they should be divided. full-size permutation, yes or no? Everybody's in, it's not like some of them are not getting a seat. Everybody gets a seat. When we have those full-size permutations, we call them very often arrangement. So the only question is who sits where, not whose choice. How many different ways that they have, and how many ways can they be seated? 6 factorial. Is everybody okay with that? Because that's exactly P of n. P7 times P7, 7. So let me erase the board and let's start this problem. So that's general one. So we said there are 6 seats for 6 persons. So it's not, so it's P of 6. By the way, if you want to get quick to these factorials calculated, you can get them on calculator. Do you know where to find them on calculator?
Yeah, it's in math.
Good. Yes, there is a math probability, so going to math, probability, and then there is factorial, NPR, NCR, so all those formulas you have a quick on there. And that's also useful for analysis. Number 2. And here it is, suddenly they will start making restrictions. In restrictions, you cannot call formula, you have to adjust, prepare your calculation, and then call formula. What is it? In how many ways can they be seated if person A must sit on the seat number 1 and person F must sit on number 6? So here it is. Here are 6 chairs, and here they are. I would like to draw this imagining like I'm really doing the process and not call formulas. So A must be here, so no ambiguity there. What else? F must be here. So what happens? No freedom here. So the only freedom you have now is what? How to set these 4 persons on 4 seats. Do these A and F influence the process at all? No. So in how many ways can we solve this? 4 factorial. So what did I do? I actually used my factorial again, but I had to adjust it according to this formula. So that was simple enough. Part 3. It says, how many ways can they be seated if A and B must sit next to each other? Yes. So what? So, first, if they want to sit together, I have to decide who sits left, who sits right. Is that a good idea? Let me see that A on left. Sitting is AB, not BA. A first, B second. Okay? And they must be next to one another. Then what can happen with AB? What could happen? A on first. Agree? And then what about B? B has to be on second. And then the other guys, whatever they want on those 4 chairs. So how many ways? 4 factorial. Which is 24. And then what? Then I can just push that by 1 C, A and B here, and then what happens? Same thing basically, don't you agree? So what would that be? 24 again. Then if A, B are here, 24, and then how many ways is that?
10. Well, there's 5 there.
5. So A, B on the last. So A is shifted from 1 to 5 because it cannot be past 5. So 1 to 5. This happens 5 times. So they are all the same. 24 times 5, which is 120. Do you agree with me? As I said, once we recognize the pattern, so we are careful with the first one, then we recognize that nothing changes along the way. So we just repeated that 5 times. Yes.
Isn't that 5 factorial?
Yes, it is. Yes, very interesting. Yes, you're absolutely right. Maybe that's something. Just a second. Let me finish the problem. So, and then I saw, this is only AB configuration. What about BA configuration? Is it also 120? Yes. Now, be careful when you do that, those 2 cases. Is from B and right from B. Could that happen? No. So that means there's no overlap, so I can freely add this count is 240. Is everybody okay with this solution? Now comments or questions or whatever.
Yeah, I was wondering if we can use permutation multiplied by combination. Combination is used for the order of AB that we have. So C2 for the variation of AB, so that we multiply that number to the permutation we have.
But which permutation of what? I didn't have permutation. I had here tons of permutations. Permutations on one line, permutation on second, permutation on fifth line, then I multiplied by 5. Then Bijan said, oh, this looks like 5 factorial, but I wasn't allowed to use 5 factorial because it's a special configuration. Don't you agree? But then he was right, actually, but you have to make a design justifying your configuration. What is that? We can think of it the following way. Instead of thinking of 6 persons, since those two don't want to separate, you know, I'll take a bandage and put it around them and put a little masking for Halloween, and that will be one big person. And that's a B person. And there is C, D, E, F. And then what do? I can say, wait a minute, but how many chairs do they need? 1 or 2? 2, but I'm thinking like this. And now I'm shuffling how many persons? Doesn't matter big or small. 5. So that's 5 factorial. Where of course, if AB is on the first, they will take 2 chairs, not 1. If they are on the second here, how many chairs do they take? 2 and 3. 2 and 3. And so everything the same as before. So that's just 5 persons, 5 factorial. But then what? Within the bandage, they can always move who takes left, who takes right. So 2 times 5 factorial, that's how I've heard yours. So can we do it with 1 line? Yes. So, but this was a nice design. But generally, you have to make a design where you justify that how are you treating that double person as 1 person? Will that make special constraint of your configuration? The answer is no, everything's fine. So of course this is quicker. Always those quick solutions are dangerous. You forgot something, you make restrictions or you make overlap. So be careful with those elegant solutions, but of course it's always pleasant. Then that was, yes, number 3. What was number 4? It's the other way around. A and B are not friends anymore. In how many ways can they be seated if they must be separated?
I'm not sure, but it seems like we can approach this by finding how many ways they can be seated, which we already did, and taking away the ones when they're together.
Very good, very quick. So that's always powerful trick. Going to the complement. Sometimes complement is easier. So generally what? In this problem 4, I'll say the following. There are how many? 720 is the whole set. And that is A union B. A are configuration when they sit together, and B, so this is together, and they're not together. There's no overlap, so then what happens? If I count those that are together, that we know are what? 240, and I remove, so I get what? Cardinality of B is 720 minus 340, and that will be 40. And that was the case. Alright. Oh, this is a neat one. and D, I can repeat a story from previous problem for C and D was the same
Yeah.
way, and then it doesn't matter. What did I ask? Two of them must be separate, two of them, so two specific ones, maybe I wasn't, so it doesn't matter A and B or any other, same way. Fixed two together, 240. Fixed two must be separated. Okay. How about number 5? In how many ways can they be seated if A must be seated before B? I cannot go permutations here. See the restriction? So if you can break it into permutation, that's fine. A ahead of B, or just before?
Farthest to the left?
Yes, before B, yes. So if seats are 1, 2, 3, 4, 5, so it means before in the line. So if this is 1, 2, 3, 4, 5, 6 to the left, you're right. On the smaller seat number. Yes.
You actually did that with the coins earlier, didn't you? You had the two tails, and you said you want one tail to be on the left, and you want the other one to be on the right. And
Not really. No, because I didn't insist who's ahead, or you mean the order is not important, something like that.
so you could assume that B would be on 6, and then A would have 5 options. And then if B was on 5, A would only have 4 options, and so on.
Yes, and then you can add them up and do the con.
I was gonna say that, kind of did that with 3, where you had, you found all the possible ways that you get seated before you.
No, in this is A and B together. So not before, because later on I flipped them. So here the accent was to be together, and here to be before. Before, they could A be on 1 and B on 6? Yes, and that was not allowed here. Yes.
Can I still have a question about number 4?
Oh, but we finished this. No, because you cannot go back and forth. I absolutely agree to go back, but let's finish these while you are. You know, I would give you a nice answer, 360. And that's really nice. But why? Just look at it. However you see them, I agree. When you count all these 720, in some of them, A will be ahead of B, agree? In some of them, B will be ahead of A. Is there any reason that one of them we have more than the other? If A and B are different. So in half of them it will be ahead of D, in half of them it will be after B. Don't you agree? That's what we say, we use the symmetry. So we'll say the following, just a second. We'll say the 720 is, so again, configuration 1, union configuration 2. In configuration 1 is A before B. In configuration 2 is B and then somewhere later A. As I said, why are these two sets have equal cardinality? Because if I flip A and B, it should be the same count, agree? And there is no overlap, so those two must be the same because of the symmetry. So each of them is what? 300. This looks like a little, when you make a solution like this, you are never sure if you forgot something important. This is legally is fine. But what was your comment, John?
What happens if we have an odd number of basic flips? Say this were out of 5 instead of 6, would that still work?
Factorials are even anyway, because you have 2 times 3 times 4, so you can split factorial of all of that. 7 factorial is still an even number, so you don't divide 7, you divide 7 factorial. So, of course, if you prefer more organized, I don't know if that's more organized, this is just more kind of safer proof at least. Then what can you say? Exactly as Bijan commented, A must be ahead of B. So if A is on first, then B has all the options in the world. Do you agree? And that's what, 5 factorial. If A is on second, then what happens with B? 4 factorial. And then you have 3 factorial, 2 factorial, and then 1 factorial. Do you agree? And then if you add them up all together, 5 factorial is 120, 4
The letters before A.
So A, if A is before B, A is on first, that's 120.
You're missing letters. You only have
Whoa, 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 no. If, what did I miss here? If A is here, then what can I do? No, that was bad counting here, it's not for factorial. Sorry. So here I have full freedom. Here, when A is here, then what should I say? First, you always host the one that's tricky. Who is demanding here? Is B demanding? Yes or no? B has to be placed somewhere here. How many options for B do we have? 4. Once you host B wherever you want, now you get freedom for the others, and that's times 4. And then
That's
if
three factor, right?
No, because there's a space.
No, there's
to
one
activate.
before.
Yes, there's also one space here now. You feed the others 4 places for people. As long as you set A and B the way that your configuration works, then you have full freedom. And then if A is here, then what's the difference?
We have.
So 3 for B and the others 4 factorial. 2 ahead, 2 above, whatever you want. And for B, just limited number of choices. 4 factorial, 1 times 4 factorial. And then what is this? I can say that this is 5 times 4 factorial. I can factor out 4 factorial. 5, 4, 9, 12, 14, 15. 4, which is what? 24 times 15. That's 360. But here is a more kind of detailed calculation where we want to make sure that we didn't forget something. All right. Oh, yes. I did mention both solutions in the notes. Yes. Well, this was an important move here. When I chose A, I first hosted B. Do you understand why that's important? Because for B, you know that you cannot, you have to keep in mind, keep it on the right, not on the left. Once you feed B, then for the others, just feed in however. We have full freedom, no restriction. So you first satisfy restrictions, and then you qualify for the